Okay. Again, we're going to do instantaneous rate of change, but this time we're going to use a formula that's a little different. Average rate of change formula we're going to use. And what we're going to do is we're going to do using preceding and following intervals to solve this. Now this question is the exact same one as we've just done. We have our formula here. And they want us to find us the instantaneous rate of change at t equals 4. Okay. We're going to find out following t equals 4 and preceding, which is going to be a lot of work. So when I say following, in other words, I mean after 4. So following, what we're going to do when using this is let's call x1, or f at x1 and x1. Those are our actual 4 and whatever the y value is when we put 4 into this equation. Our x2 are going to be points that are extremely close to 4. So a point that would be following 4 and extremely close would be something like 4.001. Okay, so that's following 4 and extremely close. So that's going to be our x2. Okay, this guy is our x1. And then preceding, a preceding interval that is extremely close to that would be, and again, it's going to be another x2. We're going to have to do this formula twice, one for following, one for preceding, would be 3.999. Right? That's extremely close to 4, we could say. So those are going to be our x2s. In one example, we're going to use this guy as the x2. So that'll be our following example. So that instantaneous rate of change at that point, and the instantaneous rate of change at the preceding. And we're probably going to find something maybe a little different. They may not be very different, but they'll probably be a little different when we do it. So in order to do that, we have to use this formula, and we have to solve it 2 times. When t is 4, in this formula, and when t is equal to 4.001. Okay, so we'll do the first one in black. Luckily, we have to use t at 4 twice, so we're just going to solve for it once. And actually, in the preceding question, we've already solved for it. S at 4 is equal to negative 4.94 squared plus 5,000. That becomes 16. 16 times negative 4.9, I think, is negative 78.6 plus 5,000. I'll double check on our calculator, okay, just to make sure. 16 times 4.9 negative 78.4. Oh, off by 0.4. Okay, so that's 78.4. And then we're going to take that value and add 5,000 to it, plus 5,000. 4921.6. No. I did not say that number right. Let's try that again. I think it was, oh yeah, it was 4921.6. Great. That is essentially our f at x1. That's what that value is. In other words, the y value at that point. So this is a coordinate. In other words, when t is 4, y is 4,921.6. That's what we just discovered. That's our x and y coordinate. So our x1, and they call it f at x at 1, but it can also be known as y1. Okay, that's what this thing is. It's the exact same. Okay, so that's one coordinate. Now we're going to solve for following that. So in other words, s at 4.00, do 2 zeros in 1? Yeah, sure. We can always get even closer. Is equal to negative 4.9 times 4.001 squared plus 5,000. We don't want to round. Okay, we don't want to round because if we round, we're going to end up with the same stuff as before. So we're going to plug this all into our calculator in one shot here. 4.001 squared times 4.9 negative equals plus 5,000. 4921.56. 4921. So 4921.56. So there's a very small difference between those terms, but there is a difference. Okay, at 4.001, this value is 4921.56. Now I'm just going to change this into black because I'm going to do the other question in green. So just so we can have an idea of our differences here, 4921.6. So that was for following. Okay, and I'm going to solve preceding right now just so we can see that we're doing the exact same procedure. This is 3.999 So we plug it into that formula, 4.9 at 3.999 squared plus 5,000. And again, we want to be as accurate as possible, so we're not going to try to round. We use all the values from the calculator. 3.999 squared times 4.9 negative plus 5,000. 492163, let's say. 4921.63. Now I could have gotten even more accurate, right? I just rounded to the second decimal place, and maybe we should be trying to get a little more accurate, but I want to just show you how close these are really in the end. So the other coordinate is 3.999, 4921.63. Okay, these coordinates we have, we're going to be putting them into this formula here. Okay, this formula here is going to be our average rate of change. This stands for pretty much our y2. So we're going to take y2, subtract y1, and figure out the rates of change here. So I'll rewrite the coordinates just so we have reference points. 4921.6. That was our x1 and f at x1. In other words, kind of like a y. For following, we had 4.001, 4921.56. And for preceding, let's call it pre, we have 3.999.921.63. And like I said, we should probably try to be a little more accurate. But anyways, so that formula is really a slope formula, change in y over change in x. And it said to take f at x2, subtract f at x1, and divide by x2 minus x1. Okay, so we'll do this one in red so we know we're doing the following. So f at x2 happens to be this value here, and this is our x2. So we take 4921.56. We're going to subtract 4921.6, all divided by 4.001, subtract 4. When we do that, we'll get our two values. 4921.56, 4921.6, negative 0.04. 0.04. And in this one, we're going to get positive 0.001 on the bottom. I subtract those two terms. So then we divide to find out our instantaneous rate of change. Divide 0.001, negative 40. Because we rounded, we're probably going to end up with roughly the same answers. So negative 40 following. So that's our rate of change. What do we say? Red is following. Great. Then we do the same thing for preceding, using that average rate of change. So we're going to use that same formula, change in y over change in x. I'm going to write it as a slope formula, just so you remember. It's y2 minus y1. It's the exact same thing, x2 minus x1. That's all we're doing. We're finding slopes of 2 points that are really close to each other. So for preceding, y2 happened to be 4.92163. 4.921.63 minus 4. Oops. It's a lot of stuff to write, as we go through. 4.921.6. And all of that was divided by 3.999 minus 4. So we put it in our calculator again. I think the difference there is just going to be 0.3. But 4921.63. Oh, shoot. 21.63. Subtract 4921.6. 0.03, 3, and then we do 399, subtract 4, subtract 4, negative 0.001, 0.001. So we divide those two terms, 0.03 divide 0.001, negative 30, okay? We got negative 30. Well, considering this point, were supposed to be extremely close to each other, notice our rates of change are very, very different. One of them is a rate of change of negative 40, and the other one's negative 30. If that was a slope, those slopes are pretty different in terms of the rate of change. So this is not quite as accurate as when we found instantaneous rate of change using that quotient difference. Okay? Another way you might do this is sometimes they take those two values and divide by 2, and then you find the average between them. And the average between those, I'm just going to go quickly, negative 30, negative 40 would be negative 35. Okay? And if you remember in the other question, though, when we did this, our instantaneous rate of change was 39.2. Okay? So one of them was actually a little closer than the other. When we used a very accurate one, we actually got a value of negative 39. Where this one, negative 30, that's actually pretty far away. So that's why the quotient, or the difference quotient, is a little more accurate than using our average rates of change. But this is that idea of proceeding and following with using average rates of change.